Hello everyone, welcome back. In this video we're going to take a look how to implement our own stack using linked list data structure. In the previous video we defined a stack and also we saw how to implement our own stack using array structure. Basically a stack data structure is a linear data structure like array and linked list. It is used to store collection of elements of same type, but a stack data structure accompanies a principle, a different rule or a principle known as LIFO or last in first out principle, or we can call it FALO or first in last out principle. The item inserted first in our stack will be the item popped or removed last from our stack. Before talking about stack implementation using linked list, let's talk about a stack data structure as ADT or abstract data type. Basically, ADTs are very popular in most programming languages. A stack is also an ADT in C#. Since we are using C#, C# comes with a built-in abstract data type called the stack. We can use it is basically a generic type. We can define our own type. Say I want to build a stack of integers, I can use the built-in stack ADT provided to us. What basically abstract data type is, an abstract data type or ADT is a high-level data structure like a stack that provides or defines the data and the operation that can be performed on that data. We don't need to know about how the stack basically is implemented. We only need to know what operation we can perform on the data we pass in our stack. In other words, it describes basically an ADT describes what can be done on data, not how the operations are carried out. It encapsulates the data and provides an interface for the user. For example, we also saw how to implement our own stack data structure. What we basically do, what we did is we created a class, and inside this class we abstracted all the implementation details and we provided some interfaces or public functions for the user to push the data in our stack and also to pop or remove a data from top of our stack. We also give the ability to the user to take a look at the topmost element of the stack. So the user doesn't need to know what data structure we used behind the scene to implement the stack or my stack data structure. So, and if we take a look at this diagram, it basically encapsulates the implementation details of an abstract data type or ADT. It only provides some interfaces through public functions. So behind the scene, we can use our own data structure, either array or linked list, to implement, for example, a stack data structure. The user doesn't need to know how these operations are performed and how the stack is basically implemented. That's why it is called an ADT or abstract data type. It basically abstracts the implementation details from the user and provides only whatever the user needs to do on the data. For example, if we consider the stack ADT, the data is homogeneous, means we can only store data of the same type in a stack, and the operations we can perform, we need to only know we can push elements to our stack, we can pop element from our stack using this object or reference variable we created. We can take a look at the topmost element of the stack using peek. We can check if the stack is empty using the isEmpty function, or if the stack is full using the isFull function. But we don't need to know what structure basically behind the scene is used in this stack implementation. That's why these stacks are called ADT, or these data structures are called ADT or abstract data type. So let's jump in and take a look how to implement our own stack data structure, this time using a linked list. As we saw in the previous videos, a linked list is basically made up of different nodes, and each node are connected to each other via pointers or links. So if we take a look at a node of a linked list, mainly a node in a linked list is made up of two parts. We have a data part. We also have a link part, which is going to point to the next node in our linked list. Say I want to insert number 4 in my linked list, so I can insert 4 at the data part of a node, and initially the link part of a node will be null, it's not pointing to any node. Say I want to insert another number in my linked list, so I can create a new node having the new number. Say I want to insert number 3. So initially the link part of this new node will also point to null. I can either insert this newly created node at the beginning of this linked list, or I can either insert it at the end of the linked list, or I can, if I have many nodes, I can insert this newly created node somewhere in the middle of the linked list. We saw all these in the previous videos. If you don't know about the linked list implementation and linked list data structure, please watch this playlist to learn more about linked list data structure. So what we are going to do in order to implement a stack data structure using linked list, what we are going to do, we will bring some limitation to our linked list implementation. We will make our linked list to follow the LIFO principle, or last in first out principle. We shouldn't be able to insert at the end of the linked list or the middle of the linked list. We should only be able to insert at the top of the linked list or the top of the stack. So we are going to limit the operations we can perform on the linked list data structure, allowing the user only to access the element from the top of the linked list, either the end of the linked list or a beginning of the linked list. We can either select the beginning of the linked list. Say we have a linked list having multiple nodes, each node are connected to each other. Say I have this linked list. Implementing a stack, I can either select this side of the linked list as my top of the stack, or I can select this side of the linked list as the top of the stack. For the simplicity of this video, we are going to select the beginning of the linked list as top of our stack, because whenever we want to insert at the beginning of the linked list, it is going to take big O of 1 or linear or constant time complexity. If we want to insert at the end of the linked list, if we don't have a till pointer here, we need to traverse over the linked list until we reach at the end of the linked list to insert a new node at the end. In that case, it is going to take big O of n, or we can reduce this big O of n to big O of 1 using maintaining a till pointer in our linked list, which always points to the last node in our linked list. So in this video, we're going to select the beginning of the linked list as top of our stack. So what I'm going to do is first I'm going to create a class that represent our stack using linked list. So I'm going to right click here, let me go add a new file. So let's call it this time my stack. I'm going to give it linked list or LL. For a linked list to represent a data, as I said, a linked list is made up of nodes. What I need to do is to create a node for my linked list. So I will create a node having a data part and a link part. So let's go here and first create a node. I'm going to add another class. Let's call it node. This node is going to have a private, let's have and let's call it data. So also it's going to have a link part properties. The link part is going to be of type node, since it is going to store the address of an object which is of type node. Let's call it next or next node, which has a getter and setter. So inside my linked list implementation, what I'm going to do is first I will maintain a private top pointer or head pointer to my linked list. So node, this is going to be of type node. Let's call it top. In the constructor of node, let's build a constructor for this also, so the user can pass the data here and data. What we are going to do when we create a node initially, we are going to set this dot data equal to data. Also, we are going to set the next pointer initially point to null. So this dot next equal to null. What we are going to do inside our linked list implementation, when we create a my stack using linked list, so let's build the constructor public my stack using linked list. So what I'm going to do is I will set this dot top initially equal to null. So when we create our linked list, initially we don't have any data in our linked list, so the top is null, means the linked list is empty. So if I create my linked list, let's call it my stack linked list is equal to new my linked list stack. I'm going to remove all these lines of code. So right now our stack is empty, we don't have anything. So let's implement the isEmpty function here. We won't be having a isFull function for linked list implementation, since a linked list is a dynamic data structure. It dynamically grows as we add the elements to our linked list. So we don't have to worry about stack being full unless we want to limit the number of elements for the user to insert. Say if we want to insert only 10 numbers, so we can have a counter here. Otherwise, linked list is a dynamic data structure and it can grow and we can add as many items as we want. So we going to implement the isEmpty function. Public, it's going to return a boolean isEmpty. It's going to return true if top is equal to null, otherwise it is going to return false. So right now our linked list should be empty. If I print here is empty, it should return true. So is.isEmpty, it should be, yes, isEmpty is true. So what we are going to do, we are going to implement the push function so that user can push data in our linked list. So I'm gonna say public, this is going to return nothing, let's call it push. This push function is going to take a data. So the first thing what we are going to do, we will create a node using this data. So let's call node, let's call it new node equal to new node. We pass the data to the constructor of this node class. So once I created a node here, say I want to insert number 1, 5 and 3 in my linked list, so I will call the push function. The push function is going to create a node here. Initially the next pointer of the node will be null, and also we set the data to the data part of this node, so 1 will be inserted here. Also in our stack implementation, we have a top pointer. Initially this top is pointing to null. So if the top points to null and we don't have any node here, so we are going to make this top point to the new node. So we have also a reference variable called new node pointing to this newly created node. Say this node has a memory address of 100. So what we are going to do, we'll check if the linked list is empty or if the top is equal to null. If is empty, so this newly created node will be our top node. So what we are going to say, this dot top equal to new node. So we will bring our top pointer point to this new node. So I'm going to bring it here and create our linked list. Say this node has memory address 100. We inserted 1 and initially this is point to null. We brought our top pointer point to this new node since our linked list was empty. So right now we have one node in our linked list, or one element in our stack. The top of the stack is this one. Say I want to insert another number in my stack, so I will call again the push function. The push function is going to create a new node with the same data. So I'm going to put it here since we will insert at the beginning of the linked list. So I will create a new node using number 5. Initially this will be null, and we will have a new node pointer will point to this newly created node, new node. So what we are going to do, we will insert this newly created node at the beginning of our linked list. In the previous video we saw how to insert at the beginning of the linked list. So first we are going to set this new node's next pointer point to the top. I will establish this connection. Then we are going to update our top pointer point to this new node. So we will bring our top here. After that we will bring our top here. Right now the top of our stack is going to be number 5. So let's do that. If the linked list is not empty, in the else block, what we are going to do, we are going to insert the newly created node at the beginning of the linked list. So we will say first new node dot next equal to this dot top. So the initial top will become the new node's next node, and then we are going to update our top pointer, make it point to newly inserted node in our stack. So this dot top equal to new node. So this way we can insert an item at the beginning of the linked list or our stack. So let's do that. So I will say s dot push. Let's push number 2. Right now number 2 is the top of our stack. So let's implement another function. We had peek. I'm gonna close this one. The peek function is always going to return the topmost element in our stack. So I'm gonna say public Let's make it nullable. It's going to integer, return an integer. Let's call it peak. So first, if the linked list is empty, we are going to return null. If is empty, or if top is equal to null, we prompt the user under flow stack is empty, and we return null. Otherwise, we are going to return top this dot top dot data. So if we take a look at the peak here, peak plus is dot peak. So right now, since we have only one item in our stack, number 2 should be the peak element. Peak is 2. If I push another element in my stack, say I want to push number 4, so 4 is going to be the top of the stack, or peak element. Yep. And is empty is false. So the next operation, we had the pop operation. Let's add another node also in our linked list or in our stack. Say I want to insert number 6. So first I will this new node is going to point here in n, or new node, to insert it at the beginning of the stack, or the top of the stack, or top of the linked list. What we are going to do initially, we'll say new node dot next equal to top. It's going to point to this node. Say it's going to store memory address 100, and this may have memory address 200, so 200 will be stored here, and this also is going to have a memory address, say 300. Then what we are going to do, we will say new node dot next equal to top. Then we will update our top pointer, make it point to the newly inserted node in our stack, so top comes here. If we want to implement the pop function, or removing the topmost element, we are going to remove from the beginning of the linked list. We saw how to remove from the beginning of the linked list. What we are going to do, we will make our pointer, top pointer, point to the second node in our linked list. Then we are going to detach this node, and this node will be eligible for garbage collection. So I'm gonna add another function in our linked list. Let's call it public. It's going to return the integer value popped, or the item popped from our linked list. I'm gonna make it nullable. Pop. First, we are going to check if is empty. If the stack is empty, we are going to prompt the user under flow the stack is empty. And we return null. Otherwise, we are going to remove from the beginning of the linked list. We are going to just update our top pointer. We'll say this dot top equal to this dot top dot next, and the initial top will be eligible for garbage collection. But before deleting that, we are going to maintain the data part of the top so that we can return it. So I'm going to use a variable. Let's call it int top equal to this dot top dot data, and finally we are going to return the top, or the top value. This should be pop, the first element. So let's also add a print function in our stack implementation, so that we can print the elements of the stack. We saw how to print the elements of a linked list, so we are going to do that. Public, let's call it print public void print. If a stack is empty, we are going to prompt the user, and we cannot print anything. Since it is void, we don't need to return null. Otherwise, what we are going to do, we will maintain a temp pointer node temp equal to this dot top. We will say while temp is not equal to null, while temp not equal to null, we are going to loop through the linked list and print the data of each node. While temp not equal to null, we are going to say temp dot data, and we increment our temp pointer, temp equal to temp dot next. So let's print our linked list here. S dot print. It should print 2 and 4. The top of the stack is 4, and the 2 is after 4. Say I want to insert number 5 or 6. 6 should be the new top. peak is 6, we have 6 at the top, then we have 4, and then we have number 2. Say I want to call the pop function is dot pop. It should delete number 6 since 6 is the top of the element, and number 4 again going to be a top. So peak is 4, 6 is gone, and we have 4 and 2. Let's call pop function 2 times. Linked list should be empty. Underflow stack is empty. We don't have anything in our peak. We can also add a size to our stack so that we can know how many elements we have in our stack. So let's comment out these lines of code, and in my stack implementation I'm going to maintain another variable. Let's call it private int len, which shows the length of the stack or the size of the stack. So this dot len initially is going to be 0. So each time I push an item in my stack, what I'm going to do is I'm going to increment the len variable len plus plus, and we can also add a function here. Let's call it public. This returns integer. Let's call it get size, that returns this dot len. Here we can say size is dot get size. Also, when we pop an element from our stack, we should decrement the size variable or the len variable. So before returning, what I'm gonna do is I will say this dot len minus minus. Let's run our code. Size is 3. We have 3 elements. So say I want to pop an item, so the size should be 2. Yep. So this way we can implement a stack using linked list data structure. Thank you guys for watching. If you guys have a question, please leave your question in the comment section of this video. I'll get back to you guys as soon as possible. Also, please don't forget to subscribe for future videos. Thank you guys, and see you in the next video. Bye bye.